Forgot about that. That's okay. All right, so this is a first question. The first question is about combinations and probabilities. So the setting is you're a high school history and math teacher. In order to make both subjects fun, you decide to make a game that involves both. You start with a pool of 6 U.S. presidents and two famous people who are not U.S. presidents. For example, you may have the following people in the pool. So in this case, we have the 6 presidents, from Richard Nixon all the way to Barack Obama, and then we have two non-presidents, as far as I know, which are Albert Einstein and Arnold Schwarzenegger. So from this pool, you generate a stack of cards. Each card has 5 names chosen from the pool. Ordering is considered important. How many cards do you generate? Be sure to explain the reasoning and how you derive this answer. Insert your answer right below this paragraph. Basically, when I say your answer here, that means you can insert your answer right there at that point. Explain how you come up with this answer in terms introduced in class, such as experiment, trial, outcome, with or without replacement, order significance, and so on. All right, so now we have to read the question more carefully, right? So this is the pool, and what you're doing is you're generating a huge stack of cards. Each card has 5 names chosen from the pool. And I didn't say how to choose those 5 names, right? So I didn't restrict those 5 names to be only presidents, or those 5 names must have the two non-presidents, or so on. So I'm really just saying, choose any 5 cards out of how many? Out of 8. And also in the question, it specifically said ordering is considered important. Okay, so in the answer, what you need to do is to explain, that we are choosing, right? So there are 5. Each experiment has 5 trials because we are choosing 5 names from the pool. It is without replacement because it's kind of implied that one, because I'm not gonna. I mean, it just doesn't make sense, to basically choose the same person twice, out of the pool. So it's without replacement, and ordering is significant because it states right here, ordering is considered important. Okay, so that's kind of spelled out already. Okay. So I want people to identify, the really kind of important portions of this. So now that we have 5 trials without replacement and ordering is significant, then the remaining question is we are choosing these 5 out of how many, right? So now we can say choose out of 8 possibilities, right? So out of 8 possibilities. So now the answer, okay, so the number of permutations this time, because permutation is the one where ordering is important and it is without replacement, and then combination is kind of like permutations, but ordering is not important. So the number of permutations is permut. We have 8 to begin with. We are choosing 5. And in this case, because you are all using a computer to do this, I want you to give me the actual number. If this were done on paper, most of the time I would say, yeah, you guys can just give me the closed form equation. But in this case, because we are all using computers to do this, it's not difficult to start up a spreadsheet. I'm just gonna pull the spreadsheet over here so you can see. So we are using a permutation, and I believe it is 8, 5 like that, and the answer is 6,720. So the number of permutations is, which is 6,720. So that would be the answer to the first part of the question. Let me see if there are any questions in class. I'm not seeing any. So I'm gonna assume that people are doing okay at this point. Oh, here comes a question. Very good. All right, so the question is, would looking at probability questions and example in 2S be a good idea to study, that is? I'm not sure. Exam 2, did we have probability in exam 2? Yeah, I didn't think so either. Oh, you mean the other practice exam for exam 2? I don't know. I guess more exposure is always a little bit better. Um, but the key idea is really just to have a very thorough understanding of the concepts involved, and basically be able to identify from a problem description, which type of probability and which type of counting we're doing. Yeah, I think that's what we had, CNF and relations. Okay, Robert has a question. If any of the conditions were different, like with replacement and ordering is not important. Well, okay, so this is the important part, right? Because um, the concept of permutation is all about without replacement. Okay, in other words, once you have chosen one option, you take it out of the bag, so that option can no longer be used again. That is why the permutation equation is how it is defined. So the answer to that question is in the discussion and also the module that I wrote about counting. So I would refer back to that module to try to answer that question. We still have Wednesday, okay? So if you guys go back to study that module and still cannot quite figure out what I'm talking about in the module, we can clarify those concepts on Wednesday. Yep. So the idea is to understand when to use which one, and I cannot just give you an answer because I want you to think about it because you gotta you have to really kind of study, read it, and then understand the concept, and then make the decision of which way should I go given the description of the problem. Okay. Alrighty. So without any further questions, we're gonna move on. Yeah, you send some of these cards to students and ask them to characterize the cards. So what we see, each card basically has 5 names, and those 5 names are chosen from these 8 people in this case. Um, and ordering is significant. Okay, so I can give you an example. Okay, some people may get Gerald Ford, Ronald Reagan, George Bush, um, Albert Einstein, and Arnold Schwarzenegger. Okay, so that's one particular way, but things can be out of order too. So another person can get Barack Obama, can get Ronald Reagan, George Bush, Richard Nixon, and Arnold Schwarzenegger in that specific order. So the ordering it can be all kind of jumbled up because there's we just basically randomly pick 5 names and ordering is important. All right. So you got a whole bunch of cards, 6,720 of these cards. You send some of these cards to students and ask them to characterize the cards. We'll get to the characterization later. The number of presidents on the card can range, okay, from 3 to 5 in this case, and that makes sense, right? This is just me, you know, uh, restating kind of the obvious because you have 5 cards, and out of the 8 people that you choose from, 2 are non-presidents. So in some cases, you end up you're choosing both of those non-presidents, and then the other 3 they have to be presidents. But in some cases, you can choose 5 out of the 6 presidents and not even have a single one of the non-presidents. So that's why the number of presidents on the card can range from 3 to 5. Let us consider the stack of cards called S4, where it contains and only contains cards that have exactly 4 presidents. All right, so we got a point here. Oh, okay. Thank you, Anita, for posting the link to the counting module, because that is relevant to this particular question. All right, so this paragraph, all it does is to describe that we now have a stack that I call S4, and S4 contains only the cards that have exactly 4 presidents in any particular order, and there's no limitation of which non-president is included in the stack of 5 cards. So this stack of cards still has 5 names on it, of which 4 are presidents. All right, so in the exam, if that part is not clear, you can always ask clarification questions. So if someone says, okay, so is S4 a stack of cards with only 4 names, or is it a subset of what we have been talking about, where we basically have that has 5 names on it? Okay, so that's a pretty good question to ask, and I am going to make myself available the entire time during the final exam. So if you need clarification, it is not a problem. On the other hand, if someone asks me how to solve this problem, or ask me the differences between permutations and combinations, I cannot answer those questions during the exam. So knowledge questions I cannot answer, clarification questions I can answer. And some people are pretty smart. They will try to cast a knowledge problem as a clarification problem. I can tell those things apart too. So not trying to discourage people from asking questions. I'm just saying that I may say I cannot answer that question for certain types. All right. So next paragraph. Given any card, not just from stack S4, a student evaluates it in number 1, how many of the names are actually presidents, and 2, whether those names are in the correct order or not. So in the correct order simply means that they are in the correct chronological order. They don't have to be contiguous. In other words, if I give, in the case of 3 names, okay, I'm just using that as an example. If it is Richard Nixon, Jimmy Carter, and Ronald Reagan, that will be in order. Okay, even though we skip Gerald Ford in between, it is still in the correct order, because Richard Nixon is before Jimmy Carter, and Jimmy Carter is before Ronald Reagan in terms of their presidency. So that is what it means when I say, whether they are in order or not. Okay, just being in order doesn't mean that they have to be contiguous, which means they have to be serving successive terms without anyone in between. So I just want to make that clear. All right, so the characterization involves 2 parts. Okay, the first part is to identify how many are presidents, and number 2 is to identify whether the presidents mentioned are in the correct order or not. So that also means you can have interleaving of non-presidents, okay? Because when we look at these, so if I have a deck of cards or a single card that has Jimmy Carter, Albert Einstein, George Bush, and Barack Obama, that will still be in order, okay? Because if I don't count the person who is not a president, all the presidents on that card are still in the correct order. So I just want to make that clear. So when you answer questions like this, and you have a question of, okay, but how does that count? Does it count as in order or not? When we have a non-president kind of in the in a bunch of presidents, that it should not matter, because we are only looking at the presidency terms of the presidents. So when you have interleaved non-presidents, that would not actually change the ordering of the presidents. All right, no questions so far. So you can think of a student's characterization of a card as a 2-tuple NB, where a number of presidents is n and B is a Boolean value of whether the precedents are sorted in an increasing order based on terms. And just to make it interesting, this is how a particular card is scored, how an answer to a card is scored. So you give a student a card with 5 names, the student characterizes the card, and then you look at the answer, you look at the characterization, and then you give the person, the student, either a point or no point. And this is the pseudocode. If the number of precedents n is correct, then you also check whether the order of the precedents is correct or not. If both are correct, then you get a score of 1. In other words, to get a point, okay, in terms of scoring, the student must indicate that the number of precedents is correct, and the order of the precedents is correctly. And if the order of the precedents is correctly ordered, then the score is 1. I'm looking at this and I think oh, okay, I see. So this means, if the number of precedents is incorrect, so that if there are actually 4 precedents, but the student said there are only 3, then you don't even look at whether the ordering is correctly identified or not. So to get a point, to get a single point, the student has to identify correctly the number of precedents and also to identify whether the precedents are ordered correctly or not. That would give that person a point. Anything else, okay, will get a score of 0. So I'm looking at the text channel and making sure that we do not have any questions about what the question is asking. Okay, so we don't seem to have any. All right, so occasionally I will give you examples, but that takes up a lot of space and takes up time for you to read. So if you think you got what the question is asking already, then you don't have to follow you don't have to read the following. But I'm going to go through the examples too, just to make sure. So we have a card that has Richard Nixon, Albert Einstein, Gerald Ford, Jimmy Carter, and Ronald Reagan. Okay, so in this case, now you don't have to be an expert in US history because you can just look up, because the ordering is correct up here. So now we look up Richard Nixon. Albert Einstein is not a president, so we just have to make sure that Nixon, Ford, Carter, and Reagan are in the right order. So if you're not familiar with US history, you can just look it up. So we got, I think they're in the right order, right? So that means, so now we have to, so if 4 true, has a score of 1, and everything else is going to have a score of 0. Okay, does that make sense so far? To get 1 point, the student has to identify the number of precedents correctly, and also whether the precedents are correctly ordered within those. The second example has Reagan, Nixon, Einstein, Ford, Jimmy Carter, and obviously the 4 precedents are in the wrong order. So 4 is correct, is good. False is also good because the 4 is referring to 4 out of the 5 names are precedents, and then the false is indicating those precedents are not listed in the correct order. So by identifying these two, the student gets a point of 1, and then for everything else, it's going to be a 0. So now the question is, given stack S4, now remember S4 is a subset of all the possible cards with only 5 names, and this particular subset has the special property that we know that there are 4 precedents within those 5 names. The ordering is still kind of all over the place, okay, but we know for sure there are 4 precedents in it. Evaluate with step-by-step explanation the following. Insert your answer after each paragraph. So the first question is, what is the total number in stack 4? So if I just want to count the number of cards in stack 4, what is that? And then we'll call this number A so that later on we can just refer to A, B, C as a number. All right. So how do we figure this out? Okay, because we know there are 5 names, right? Of the 5 names, 4 are precedents, 1 is a non-precedent. So how would we figure this out? So the first thing that we need to do is to think about the cases where where ordering is not important, because that will help us relate this problem to the lottery problem. Okay, because we have to choose four of out of the five presidents, choose one out of the two non-presidents. So this is the first thing that we have to quickly identify, is to say, okay, every single card out of this stack is going to have four out of the five presidents. We don't know which four out of the five. Okay, we don't know whether they're ordered correctly or not, but we know there are four out of five. The remaining one has to be one out of the two non-presidents. Okay, so and then from the discussion of the lottery problem, so we now know that and I'm going to use uppercase here, in combinations. Okay, combinations. Okay, there are combin 5 4, 5 choose 4 times combin 2 choose 1. Now this technique is was used when we went through the lotto problem, because we have the winning numbers versus the non-winning numbers. So when we want to figure out how many tickets out of the total possible tickets can win a particular prize, because you can win something if you match three out of the five winning numbers, and also whether or not you got the lucky number right or not, that would also further differentiate what prize you're going to get. But in this case, we don't have a lucky number. We just want to look at the winning numbers and so on. So we have basically four out of the five presidents and one of the two non-presidents, but we'll be counting in combinations in this case. Okay, so we'll go ahead and actually use a spreadsheet to calculate this. Okay, so put a spreadsheet here. So we have combin 5 4 times combin 2 1, and that will give us 10. Okay, so you might say, but that's not a whole lot. Well, wait, there's more, right? So each combination has exactly five names in it. Of the five, four are presidents and one is a non-president. So there are only 10 ways in this case, okay, to arrange so that we have four out of the five non-presidents, and then we only have one out of the two. Excuse me, the other way around. We only have four out of the five presidents and one of the two non-presidents. And it kind of makes sense, because if you think about it in a kind of the reverse way, we just have to leave out one of the presidents, right? Because we have to leave out exactly one president, and there are five ways to leave out one of the five presidents. And then we have two non-presidents, and we have to choose one of them. So there are two ways to choose one of the two non-presidents. So intuitively, 10 makes sense. Okay. But now we have to say, but ordering is not important when we count in this way. So now we have to say, for each way of choosing four out of five presidents and one out of two non-presidents, there are permit 5 ways of ordering. Therefore, A, which is what I want to call the answer in this case, and therefore 4A is permutation 5 times combin 2 1 times combin 5 4, and that turns out to be, okay, so I'm gonna work on the math here. Now permit 5 is just 5 factorial, and I believe that is 120. So the total number should be 1,200. But I'm not going to trust my own math, okay? So I'm just going to use my spreadsheet to do the calculation. So combin 2 1, and then we have combin 5 4, and that turns out to be 1,200. So I got the number actually right the first time. There we go. And I'm reading the text channel. There are no new questions at this point, and I'm just gonna move my cursor over because sometimes Discord would crash and I wouldn't know because it's basically frozen, and then I don't get additional text messages. All right, so next question. So the next question is saying the number of cards where the answer of 4 true earns 1 point. Call this number B. Don't forget to explain and derive the answer. So we want to calculate the number of cards where the answer of 4 true out of stack S4 is going to earn 1 point. Okay, so we are still talking about the stack S4. And that kind of makes sense, right? Because it doesn't make sense, otherwise, because otherwise, the first 4 out of the 2 tuple wouldn't make it would not earn a point. Okay, so we have to be talking about the stack S4 in this case. So in this case, we are looking into the cases where the ordering is correct. Okay, so we out of the 1200 cards, okay, where we have 4 out of the 5 presidents and 1 out of the 2 non-presidents, we now want to count how many of those would have the ordering also being correct. All right, so that one, okay, so we basically just have to say, let's see, I'm thinking here. Okay, so I'm just thinking about which way to explain this would be the cleanest. Because there are 2 ways to look at it. The first way is not to worry about the combination. In other words, we don't even bother to reuse the way we calculate A over here. And I think that probably is the best way to do it. Okay, so I will just go ahead and go with that one. Okay, so we basically just have to say there are 5 combine 4 ways to choose 4 presidents out of 5. Okay, so Anita is asking, so we are trying to find how many times the cards can be 4 true. Yes, exactly. In other words, we have 4 presidents out of 5, and the presidents are in the correct order. Okay, there you go. Good job. So now we just have to say there are 5 choose 4 ways to choose 4 presidents out of 5. Okay, that's something that we talked about already. And if you want to explain further, you can always just kind of repeat what we said. This is without replacement. Okay, and in this case, we are not talking about permutations. We are talking about combinations. So we can kind of make it very clear in combinations. Okay, but we can also now state each combination only has one permutation that is in the right order. Does that make sense to you guys? If I did for each way of choosing 4 presidents out of 5, there's only one permutation that has the presidents in the correct order. Okay, so that means so now the only thing that we have to do is to figure out the number of ways that the non-president can interleave with the presidents. Okay, so now we say the number of ways the non-president can interleave with the presidents is. Alright, so in this case, I want to be general, okay, and not just, because when there's only one, it's easy to figure out. But what about when there are 2, right? So, so now we have to think about the non-presidents, okay? If they're plural, if they're there are multiple non-presidents, now we have to think about how those can interleave with the presidents. And the way we do that is to look at the positions as a set. Okay, so the way we look at it is to look at the positions as a set, and then we look at how many of those elements in the set can belong to the non-presidents, and then that would be the starting point of this whole thing. So the this is basically permit, in this case, 5-1. Okay. The 5 is coming out of the total number of positions in the set, and then the 2 is coming out of the number of elements in the set that are non-precedents. So in this case, permit 5-1 is really just 5. Okay, we got a question here. Aiden is asking, I'm confusing about AS4. I tried to add up S3, S4, S5, didn't add up to, what? S4 is, oh, you're talking about the equation, how I computed S4? Okay. All right, so we'll get back to that one in just a little bit. Let me finish this first. Okay. And then we'll get back to what Aiden said. All right, so we have 5 ways of interleaving, and that kind of makes sense, right? Because if you think about so we'll use n as non-precedent and p as precedent. So we have n p p p as 1, p n p p p as 1, p p n p p as 1. So you can kind of, I mean, at this point, I think most people can see that there are 5 ways to interleave the non-precedent with the precedents. In the case where we have multiple non-precedents, it's going to be a permutation thing because the position does matter. Because where we put Einstein and where we put Schwarzenegger is important because we are talking about overall permutations. So in this case, the question is asking how many of the cards have exactly 4 precedents and the precedents are in the right order. So now the answer B is going to be combined 5-4, and we still have to multiply combined 2-1 because there are 2 non-precedents. Okay, so we have to. Okay, let me give you an example. Okay, we'll just use NPPP as the way we arrange the non-precedent within the precedents, and the precedents are in the right order. So what we choose for these 4, we don't really care because that's already taken care of using the combine 5-4. But the n can be Schwarzenegger, can also be Einstein. So there are 2 cards of exactly this property, and that's why we have to multiply that by combine 2-1. Now, that also needs to be further multiplied by permit 5-1 in this case, because there are 5 ways for this non-precedent to be interleaved with the precedents. So the correct answer in this case is this number, and we can go ahead and figure this out. I think this one is 50 because this part here is 10, and then 10 times 5 choose 1 is 5, so we have, that should be 50. And instead of just trusting my math here, we'll do the calculation. So we have, in this case, combine 5-4 times combine 2-1 times permit 5-1, and the answer is indeed 50. Alright, so we are almost there. The number of cards when an answer of 4 false earns a point, called this C. Explanation and derivations are required to get full points. Now this one is easy, okay? Because this is referring to all of the other ones, okay? So basically we have, once again, we have combine 5-4 times combine 2-1. That would be the number of combinations, of these cards, okay? Is the number of combinations. And then of these, now we have to figure out, how many of these would not have the right order. Okay. So now the question is, time, we also have to multiply by, because we still have to look at, let's see, that's interleaving. Yes. Okay, that doesn't, this is the combination, is the number of combinations. Because there are 6 precedents to begin with. Yes. Oh, okay. Right. Okay, so I got all of these math wrong. Sorry about that. Well, not all, okay, but the way I choose the number of precedents should be 6-4 because there are 6 precedents to begin with. Okay. Thank you, Aiden. Sorry about that. Because in my mind I kind of mixed up the number of precedents. So the discussion is still right, when you change all the combin 5-4 to combin 6-4. The other 5s are correct. Just the number of precedents, there are 6 to begin with, and we're choosing 4 out of those. Alrighty, so let me go back and see if I have any further. There's one more, I think, earlier. No, this one is correct. And let me see, right here. So this 5-5 is correct because it's within the 5 names that we have permit 5-5 permutations. This 5 needs to change to a 6. I'll send this file to you guys so you don't have to kind of scramble and make adjustments to your own. Alrighty. And this 5 is also correct. So that is, so the numbers will turn out to be different. Alright, so let me check out. Yes, so to answer Anita's point, yes, you will still get points if you reason it out correctly. So okay, that's a very good point because I say specifically, I made the mistake here, of where there are combine 5-4, and the 5 is wrong in this case, but I explained why I do that, and I say we're choosing 4 precedents out of 5, so so the concept is still correct. It's just that I forgot or I miscounted the number of precedents in this case, and that's why the explanation part is really important. If somebody were to just give me the closed equation, that would not be good because in that case, I cannot see the reasoning behind it. All right, so let me just change all of these so that we have the right number. There we go. Okay, so that looks better. All right, so we got to adjust all of these numbers. So instead of 1200, we have 3600 in this case. And then instead of 10, we have 30 right here. All right, so getting back to here. So we still have this many combinations. Out of these combinations, this time we are interested in the ones that are in the wrong order. So we just have to, and we also have to put the, we have to do a permit 5-5 because now we have the total number of combinations. So this part, okay, let me just explain these one by one. Okay, the total number of cards in S4 is, now this is just one of the numbers that we have calculated already, which is A. And then we have also calculated the ones that have the right ordering. Okay, so the total number of cards in S4 that has the correct ordering is B, and B is already calculated. to be, oh, okay, I'm putting my, oh, sorry, I messed up the location of my question. Okay, so let me get back to Anita's question first. How come for A we are still using permit 55? Explaining this one here. Okay, so we'll explain these in sections. So this part here is telling us how many combinations we can get. Okay, in other words, we want to somehow, ordering not being important, we want to end up with 4 precedents and 1 non-precedent on a card, where ordering is not important in this case. So that explains the combin 2-1 times combin 6-4. But remember these 5 names, so okay, so now we put those 5 names in a bag, and then we say out of these bag, we're going to choose 5 out of 5, but this time ordering is important, and that explains why we have a permit 5-5, because now ordering is important, so we have to multiply basically 5 factorial by the number of combinations in order to figure out the total number of permutations when we want to have exactly 4 out of 6 precedents and exactly 1 out of 2 non-precedents. So I hope that answers Anita's question. To do it without combinations, I think that might be a little bit harder, because if you just look at the base number, they are not they're not using the same base. Now, if we have 5-4 here, that might be a way to simplify. But since we have a 6-4, I don't think it's easy to come up with a closed form to do this. But at least, in terms of mental math, this is how what I think makes sense to me. All right, so in this case, we have 4-1. So I accidentally changed the right answer in this case. So we have so B equals 2 combin 6-4 times combin 2-1, and that without multiplication by the permit 5-5. So I think that's 30. I'm just looking on the side. Yep, so that's just 30. And then these 2 lines belong to this answer here. So I accidentally put the answer to the wrong place. All right, so this is C. C is basically just A minus B, which in this case is 3600 minus 30, and that would give us 3570 right there. Because we are still limiting to only the stack of S4, so out of the entire stack of S4, there are only 30 cards out of 3600 where the ordering is correct. Okay, so the rest are having the ordering being incorrect. So we just have to subtract B from A, and that will count the total number of cards in S4 where the ordering is incorrect, and that accounts for the false in the 2 tuple as the characterization. The permit 5-1 in B. Oh yeah, we still need a permit 5-1. Let me think. We still have the spacing, so it's 150 in this case. Okay, let me explain that. Thank you, Aiden, for reminding me. So this is still giving me just the combination, but each time I have 4 precedents and 1 non-precedent, I still have to think of the way of interleaving the non-precedent within the precedents. and that part is taken care of using the parameter 5.1, and that tells me how many ways I can interleave the non-precedent within the precedents, and that's why we have to multiply those two, so we end up with 150 in this case, which also means in this case it is 3600 minus 150, so we got 3,450 in this case. Alrighty. Okay, so are we still good? Alright. So assume a student who does not study at all makes a semi-intelligent guess, meaning the following answer has an even distribution. So there are basically six possible, six intelligent guesses, because a student, may put down some number like 2 in this place, but that would not be a very intelligent guess, right? Because we know that within we choose I take it back. We choose 5 names out of 8. Of the 8, 6 are precedents, 2 are non-precedents. So that means 3 is the minimum number of the number of precedents. If someone puts down 2, that person is not even logical. That person did not study at all, and also did not understand counting. Just simple like finger kind of counting, not combination and permutation kind of counting. So in this case, I made it very clear that we are only evaluating these 6 possible answers, because a student who did not study the history part, okay, will still be able to identify that 3 is the minimum of the total number of the number of precedents, within the 5 names, and 5 is the maximum because we do have 6 precedents in total, so that it is entirely possible to choose 5 out of the 6 precedents. So what is the average score of a randomly guessed answer of a card from stack S4? So we are still limiting ourselves to the stack where exactly 4 names out of 5 are precedents. Okay, make use of variables A to C if possible to minimize duplication of expression, and then explain your answer. All right, so we just have to look at the chances of each one being correct and see which one. Well, actually, we just have to find out which one is correct, can earn a point, and figure out the probability of that point being earned. All right, so what do you think? We got those 3 numbers. We got A, B, and C. A is referring to the total number of cards. So let's go back to the first question. Oh, I take it back. A is not referring to that. A is referring to another number. 6,720 is the total number of possible cards. So when we add up the possibilities of all of those 6 possible answers, they should add up to 6,720. And then we have A. Let's see. Okay, and then we have A being calculated here, and then we have B calculated down here, and then we have C being calculated down here. Basically, A equals to B plus C. Okay, and since we're limiting ourselves to the stack S4, what is the average score of a randomly guessed answer in that case? All right, so let's figure out 3 true. Okay, if a student is to answer with a 3 true, what is the average point value that the student will be getting in this case? Now remember, we're still specific to the stack of S4, so that would be a 0. Okay, basically anything that has a non-4 as the first item of the 2 tuple is going to get a 0. So 3 true, a 3 false is going to get a 0. So now we get to the good ones. Okay, so 4 true. So what are the chances that a 4 true is going to get the right answer? Well, in that case, it would be 150 divided by 3600, because out of the 3600 cards in the S4 stack, 150 would actually be matching 4 true, as the correct answer. And then the next one is 4 false, okay? And that one has 3,450 of those out of 3,600. And then we have the 5 true, okay? 5 true, is not going to be getting any points, because remember, we're still limiting to a card from the stack S4, which means we're still only saying we're only considering the cards that have exactly 4 precedents. But the student doesn't know it, okay? So that's the other thing that is important. Okay, so we basically have all of these things here, and this is worth 0 points, worth 0 points. This one is worth some points, worth some points, worth 0 points, and 0 points. But since we're talking about what is the average score, so we have to add up all of these numbers and then divide it by 6, because there are 6 possible guesses from the student's perspective. So now the question is, so we end up with basically, the multiplication on this side here, that's really just showing you which of these 6 possible answers we're considering. So they don't really contribute to the value. So in the end, we have 0 plus 0 plus this value, which is 150 divided by 3600, and then we have this number here, which is 3,450 divided by 3,600. And yes, I know some of you are making that observation already and go like, but Tack, that just adds up to 1. Yep, that just adds up to 1. Okay, so that means we have 1 divided by 6. So the average score in this case, if you want to give me the actual number, it's going to be point, what is it, 1 and then 6, but I mean just a whole bunch of 6, somewhere. You have to end the number somewhere, or you can just leave it as 1 divided by 6. That would be the answer to this question, to this part of the question. Whew. Yes, or you can use that notation with a dot on top of the 6. Then it's just 1.6 with a dot on top to basically mean that is the repeating portion. Alrighty. So that took a little bit longer than I thought to explain it, because I made that mistake of forgetting that I actually have 6 precedents to begin with, and I got confused here with there were only 5. So, alright, so everything is being recorded, so if you need to run through the answers again, I'll post the text file when we're done here. Next question. There are only 3 questions in this case, so this is question number 2. I'm gonna make it more clear that we have question number 2 here. Alright, so the question number 2 is kind of interesting. The following is a trace of Dijkstra's algorithm. That is posted already, Jack. If you go to the pinned messages, that's the first one is the text file without the answers. Alright, so for question number 2, we basically start with a trace of the algorithm as in the notes. So in this case, you can go back to the notes and refer to Dijkstra's algorithm in the notes. It contains most of the information that is needed to reconstruct the original graph. The only piece that cannot be reconstructed are the distances of the edges. Your answer is to figure out the original graph and propose a distance function that generates the included trace when Dijkstra's algorithm is applied. Explain your answer whenever it is appropriate. There are many ways to do this, such as plugging in numbers and trial and error. This approach is going to work really well if you are a non-deterministic polynomial time capable machine. But generally speaking, it does not work very well. Okay. However, a more systematic way and realistic way is to figure out the relationships of edge distances. In other words, we want to figure out which edge is more than which edge, or the sum of which edges are more than which other edges. As a hint, your first task should be reconstructing the edges first without considering the distances, and then figure out set S, the set of destination vertices. Once you have this done, then it will be easier to figure out how distances of edges relate to each other. Make use of the algorithm to explain how you figure things out. So this is the important part. So when you figure out things, you have to tell me, oh, because of this condition of this conditional statement, because we end up here, we know that that relationship has to be true, and now we know this sum is less than that number, and so on. Okay, so by the time we get there, it'll be clear what I mean by that. Your final answer should include a set of vertices V, the set of all the edges in the original graph E, the distance function D, and any representation is fine, as such as the set representation, or you can draw a graph, okay, and then you label the edges with a number. That is perfectly okay as well. And then you have to figure out a way to kind of take a picture and then slap it into the Google document. If you find it more useful, you can also include a hand-drawn picture, just what I said. You can insert your reasoning interleaved within the trace itself. So now here is the trace. Okay, so this trace is obviously mechanically generated. I do have one, program that can do this. So it basically just runs the Dijkstra's algorithm, and we know Q starts with N8 and 1, and then we first choose N8, and then blah 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 blah. So now you look at this trace. Okay, it looks a little bit tedious and hideous. But what you want to do, this is the next question, by the way. So this one is question number 3. Okay. So now the question is, what do you do first? Okay, when all you see is a trace. First thing, okay, is to understand how to read the trace. Okay. So if you remember, I didn't use a spreadsheet in this case, because it's harder to express the trace in a spreadsheet. So what this is basically saying is, the indentation is important. Okay, whenever we see Q equals to blah blah, and then we see Q equals to blah blah, these have the same indentation. So these are indicating what Q has when we evaluate, while Q is not empty. Okay, and then the variable V is chosen once we get into the while loop. Okay, and that's why we have one level of indentation. And then after that, we update Q, so we remove whatever we have chosen from Q, and that's why Q is now without N8, only has N1 in it. And this is the most crucial part, okay? This is the most crucial part because this is corresponding to the condition of the conditional statement, and it tells us, whether a condition is true or not. So you can see true, 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 and then we have true, true, true. Okay, and then we have false. Okay, so that condition can be true, can be false. Okay, it just turns out in this case most of the time it is true. And then over here we have an update. Okay, so these are updates. Single equal symbols are kind of updates. So this is an update, and say that we are updating the value of L of N3. Now the question is, attack, you left this as question marks. Well, that's because I want you to figure out the distances. If these are not question marks and concrete numbers, that will make the problem way too easy to solve. Okay, and that's why these are question marks. I want you to figure out the relationships first, and then you figure out the actual values. E prime is first modified by removing everything that has N3 as the start vertex of an edge, and then we replace I shouldn't say replace, and then we add the edge from N3 to N8 in this case, because N8 is V, which is we are basically backtracking to what vertices can go to vertex V. So in this case, the edge that we're considering is N3, N8. So this is also crucial. Well, okay, let me take it back. This is crucial because it tells us there is an edge, n3 and 8. Okay, so that's why it is important. And this is where we put the edge into E prime. And then after that, we have to add n3 to the set Q. That's part of the algorithm. All of these are basically, using the algorithm. All right, so at this point, what do we know about the graph? Well, we know that there are a few vertices in this graph. We know n1 is in the graph. We know n8 is in the graph. We also know that n3 is also in the graph as vertices. But we also know quite a few more things, okay? Because the initial condition of Q, okay, so I'm gonna have you guys to look into how did we initialize the set Q in Dijkstra's algorithm. Okay, so that's one question you kind of have to ask yourself. Okay, Aiden, the rest of the class, they have to think too. You cannot do all the thinking for the class. All right. Yes, so Aiden is correct. Okay, the set as which is the set of all the destination vertices. Um, oh, okay, that was quick. You can also use spoiler. I think in Discord you can post something as quote unquote spoiler. So for people who do not want to see the answers right away, they won't see it unless they click on it. Yep, there you go. Good job. Yep. So that makes it easy. For some people who just want to know the answer, they can click on it and see the answer. And for others who want to kind of figure out things by themselves, they can not click it and try to figure it out. Okay, very good. So the crucial part is this is significant because it answers an earlier question. And the other part that is also important is we know there's an edge n3 and 8 in the graph. Okay. And then we evaluate the next. So there are a few neighbors, right? So n3, n7, and n6. They're all within the inner loop inside the while loop because we have a for each loop here. So you kind of have to ask yourself, what is the significance of that for each loop? So we have identified the three edges, n3, n8, n7, n8, and n6, n8 in the graph. So remember, the first thing you want to do is really just to draw a picture first. Okay, your pictorial representation is always helpful, and you can always use your cell phone to take a picture of what you have hand drawn and turn it in. Okay, you'll paste it into the document, but you have to make sure that you have enough time to do that. Okay, so just by looking at these, comparisons, now we identify there's an edge, n5, n1, n0, n1. And now we have the edge n7, n3. Now we have the edge n2, n0. And then we have n2, n6, n3, n5, and so on. Right? This is the last one. This is n7, n2. So just by putting all of the edges into the graph, now you get to visually see what the graph looks like. Okay? So the next really important piece of information is whether the comparison, whether it is greater than, which in the notes is actually less than, but it's really, they boil down to pretty much the same thing. So whether this greater than, makes, why is it significant? Okay, because whether this is greater than or not greater than, it gives you an ordering information. So if you take this into consideration, then you end up with an ordering information. But the other thing you can also do is once you draw the graph, okay, and you work your way, so it is more important when Q has multiple items. When Q has N8, N1, before we get rid of N1 and N8, it's not really that important. So the really important part starts here when N8 and N1 are not in Q. Because we know, okay, so this is related to Aiden's spoiler, okay. N1 and N8, they have known L values to begin with. And I'm not going to explain why, okay? You're going to have to go through the algorithm to figure that out. But these guys don't, okay? These all have L values that are computed by the algorithm in the while loop. So the reason why are we choosing N3 instead of the rest of those? Now that is important. Okay, so you have to go to the algorithm and try to figure out, okay, out of the 5 vertices in Q, why do we choose N3 instead of the rest? Okay, so I'm not gonna say anything. You guys have to kind of work this out. We still have Wednesday to finish up the discussion, but I don't want to give you the answer, because if I just give you the answer, then you're not gonna go through the analysis of the algorithm, which I think is the most important part of studying, is really kind of go back and try to understand, what the algorithm is trying to say. So I really like all those spoilers. Very good. All right. So now, getting back to here. So why do we choose N3 out of this set? Why do we choose N0 out of this set? Those are all important questions. So once you understand, why we choose a particular vertex out of the set, it will make it much easier for you to figure out the value of the edges. Okay, because it will put constraints on those edges, and then you will start to see, oh, okay, I see, if I put this value over here, then it will force the algorithm to have to choose that vertex first out of Q, and so on and so forth. Okay, so I'm gonna finish this one on Wednesday, because I want you to have a chance to kind of do what I suggested. So we'll go ahead and finish this on Wednesday. We still have some time left, which I'm going to use to answer question number 3. So question number 3 is also about probability, but it doesn't sound like it. Okay, so we'll take a look at what the question is asking. So in a bag of red and blue marbles. Now, when we only have 2 types of marbles, that should remind you of something already, right? Because instead of 5 presidents or 6 non-presidents or whatnot, okay, we only got 2 things, right? So that means a marble, you can call it red and blue. You can also just call it red and not red. Okay, so that's a pretty important clue. The chances of getting a red marble is 0.1 if we randomly draw 10 marbles from the bag without putting drawn marbles back into the bag. What are the chances that 5 of the drawn marbles are red? But wait, do not answer yet. This problem is a little bit more tricky than it seems. The issue is the total initial number of marbles in the bag. All right. First, assume the bag is magical and you can draw as many marbles as you want, and the chances of getting a red marble remains the same. So imagine you have a really magical bag of marbles, and in this magical bag, when you draw a marble out, the chances of getting a red marble is always 0.1. So use the following space to explain how you get the probability. Terms that may be useful in this explanation includes experiments, trials, outcomes with or without replacement, binomial distribution, event set, omega, and so on. Okay, so let's try to answer this question. You can draw as many marbles as you want, and the chance of getting a red marble remains the same, which is 0.5. And the question is, what are the chances that 5 of the drawn marbles are red? Okay, so in this case, it is with replacement, because the how you have picked an earlier choice does not impact the probability or the availability of choices of the future ones. So this is with replacement. So if it is with replacement, and there are 2 possible outcomes in each trial, because each trial, which is drawing 1 marble out of the magical bag this time, is either red or non-red, right? So there are only 2 possible outcomes. So this means we are looking at binomial distribution. Okay, now that's a huge clue, because once we know we're dealing with binomial distribution, then it becomes go like, Okay, so the chances of 5 of the drawn marbles are all, we are randomly picking, okay, we are drawing 10 marbles. Okay, so each experiment has 10 trials. Each trial draws a marble, and we want 5 out of the 10 trials to have red marbles. And because this is binomial distribution, so we're looking at combin 10(5) times 0.1 to the power of, okay, I'm going to use the equation 0.1 to the power of 5 times power 0.9 to the power of 5. So that would be the probability that we are talking about. So we are talking about the probability of having 5 red marbles out of the 10 that we are drawing out of the magical bag. Alright, so Angel has got some comments here. So it's magical. So that means, no matter how many marbles you have drawn out of the bag, the next marble always has a 0.1 of a chance of being a red marble. That's magical because typically you do not get that of behavior. All right. So let's go ahead and plug in this equation. Okay, so we'll go ahead and copy and paste it into the spreadsheet. So you can paste in this number. Okay, I'm just gonna copy and paste the number in here. There we go. All right. Second, assume the bag has a small number of marbles, so it's no longer magical. First of all, compute the minimum initial number of marbles in the bag, so that it is possible to draw 5 red ones according to the ratio of the red marbles to the total number of marbles is 0.1 to 1. So we are talking about 1 to 10 of a ratio here, and we need at least exactly 5 red marbles to be able to draw 5 marbles out of the bag, in our experiment of 10 trials. Rounding up using the ceiling function may be needed to make sure there are enough red marbles in the bag. Okay. All right, so we need 5 red marbles in the bag because we want to be able to draw 5 out of 10 marbles. Out of 10, drawing 10 marbles, we want 5 of those to be red. So we need 5 red marbles in the bag. So using the ratio of 0.1 to 1, there are so the 1 is a total number of marbles. So there are 50 marbles in total. This means there are 45 non-red, basically blue, marbles in the bag. Okay. All right, so that pretty much answers the question, and in this case, there's no need to round up, okay, because it just it's very nice because 0.1 to 1 is a 1 to 10 ratio, so we just have to multiply 5 by 10, which will give us a 50 of total number of marbles in this case. All right, next one. Third, based on this finite initial number of marbles in the bag, compute the chances of drawing exactly 5 marbles out of 10 from the bag again. All right, but this time it is different because this time the bag is no longer a magical bag, which means we are once you draw a red marble out, you cannot draw that red marble out again. Okay, it is out. Okay. So now we have to look at this problem in a different way. So now we have to say this time, we have 10 trials per experiment. Okay. experiment. There we go. I cannot type. There we go. Experiment. And this time it is without replacement. It's without replacement because once you draw a marble out, you don't put it back into the bag. So we have just used experiments, trials, outcomes without replacement. So it is not binomial distribution anymore. This is not a binomial distribution. Okay, so if it is not a binomial distribution and you want to calculate probability, so now you have to think about what is the event set and what is omega. So omega is the set of ways to draw 10 marbles out of the bag with a total of 50 marbles. Okay, so now we have to think about, do we want to look at permutations or do we want to look at combinations? The question does not say anything about ordering because once you draw the red marbles out, we're just counting, right? Because we just want exactly 5 red marbles. The question did not say anything about the ordering of the red marbles. We just want to see if they're red or not. Out of the 10 marbles that we draw out of the bag, we want 5 to be red. Okay, so ordering is not important in this case. Okay. Since ordering is not important, we are counting combinations. So the cardinality of omega is combin 10 5. Oops, nope, take it back. 50 10, because we are drawing 10 marbles out of a bag that has 50. Okay, so I'm just doing this math on the side here. This is going to be a big number. So 50 out of 10. So we'll put this number here. Next, we have to calculate what is the event set. Okay, so the event set has elements. Okay, let me rephrase it. Each element in the event set represents an experiment where 5 marbles drawn are red. Okay, so now how do we do this? So what we do is we go back to the lottery problem. So when we go back to the lottery problem, you might say, the lottery problem is not, there's nothing that is binary about the lottery problem. Well, that is actually not the case. Because with the lottery problem, 5 numbers are the lucky numbers, right? What about the rest? They are the not lucky numbers. And that's why there's still a binary nature to the lottery problem, because we have one set of numbers that are our lucky numbers, and then the rest of all of these other numbers, they are not lucky numbers. So in that sense, we still have a binary nature to it, but it's not in a binomial distribution sense. So what we do here is we borrow the same technique, from that one. So we basically say there are combin 5 ways to choose 5 red marbles out of 5 red marbles. Okay, and then there are combin 45 ways to choose 5 non-red, well, in this case they're just blue, marbles out of the remaining, the 45 non-red, or if you prefer, blue marbles. So once we identify these, we just have to multiply, right? So we basically go like, there are combin 5 times combin 45 ways to choose 5 to choose 10 marbles, of which 5 are red. There we go. So now, but I'm not done answering the question. Okay, so we now say the cardinality of the event set is combin 55 times combin 45. And we can always do the actual calculation. So combin 55 is just 1, but it's good to write it out too. Okay, so the total number is this here. So now we can now calculate the probability. So the probability is basically E. Okay, I'm introducing. We can introduce the symbol E earlier to basically say that is the event set, and then we have to divide it by the cardinality of the omega set, and that becomes this number divided by the larger number that we calculated earlier, which is this one. And the chances obviously is pretty low. I'm just doing it on the side on my spreadsheet here. So the chances is a very small number. So it is a 0.01% of a chance. So that's the answer of the third question, the last question. All right, so we are out of time today. So on Wednesday, we're going to finish up the Dijkstra's algorithm question, because I want you guys to kind of spend some time to think about that one. It looks really complicated, but it really is not once you understand how the algorithm works, how it selects one element out of all the elements in Q. That is the biggest one. That is the biggest clue to help you determine what values you should use for those edges, or at least it will give you an idea of the ordering of the edges, so you can tell which edge has a smaller distance than which one else, and that will help you answer that question. All right, so do we have any additional questions? I'll post what I have here, okay, what I have done today. I'm going to save it and post it right now. Obviously, if you don't want to look at it, don't. Okay, just leave it in the text channel. Okay, so I'm going to say this has answers to Q1 and Q3, and upload. There we go. And I will pin this one too. All right. So my recommendation is for you guys to try to work on these problems without looking at my solution. And for questions 1 and 3, when you're done, you can go take a look at my solution. For question number 2, I did not actually disclose the solution, but I did tell you, a technique, more or less, to approach that particular question. So the algorithm, fully understanding the algorithm is still an important part of answering that question, and then we'll do that on Wednesday. All right. Oh, okay. And we'll also talk about the third question on Wednesday. Or in general, how do we know we're dealing with a combination problem, a permutation problem, or a binomial type of problem? Because those are the 3 kind of distinct problems that we have dealt with in this class. So I will talk about that a little bit on Wednesday, depending on how much time we have after explaining Dijkstra's algorithm. All right, so cool. So if we don't have any additional questions, I'm gonna sign off for now. And obviously I have a lot of grading to do, and that's looking really kind of pessimistic too, because one of the classes that I picked up that I thought I only had to teach the first 4 weeks out of the 8, looks like I'm gonna have to teach the rest of the class too. So it's going to be a little bit my workload is going to be a little bit heavier than usual from now all the way to the end of this month. So it's going to be interesting. My problem to solve, not yours. So I'm going to talk to you guys on Wednesday, and bye.